Hello students, welcome to Educate. Today we are going to start chapter number 6 of class 12 physics, electromagnetic induction. So let's see about the chapter. We have already studied about electromagnetic induction, which states that whenever there is a relative motion between coil and a magnet, in that case an EMF is produced. So here we are going to study the same thing in detail. Here the phenomena in which electric current is generated by varying magnetic fields is appropriately called electromagnetic induction. And when Faraday first made public his discovery that relative motion between a bar magnet and a wire loop produced a small current in the latter, he was asked, "What is the use of it?" His reply was, "What is the use of a newborn baby?" So, the phenomena of electromagnetic induction is not merely of the theoretical or academic interest, but also of practical utility. Imagine a world where there is no electricity, no electric lights, no trains, no telephones, and no personal computers. The pioneering experiments of Faraday and Henry have led directly to the development of modern day generators and transformers. So today's civilization owes its progress to a great extent to the discovery of electromagnetic induction. So you can say that the concept is very important, and Faraday performed certain experiments in which he took two coils. First was in which there was single coil. Here there is galvanometer. When magnet is brought closer to the coil, then this galvanometer showed deflection. Now when he took this magnet away, again there was deflection in the galvanometer, but it was in different direction. So he concluded that whenever there is relative motion can be other way around also. Suppose magnet is fixed and this coil is moved like this. Suppose it is moved closer, then there will be deflection in one direction. If you take it away, in that case, deflection will be in opposite direction. So he concluded that due to relative motion between coil and magnet, and EMF is generated in the coil, due to which this galvanometer shows the deflection, right? So there was another experiment also. Here there is one coil which contains battery, means it can conduct current. There is another coil in which there is no source of EMF, but it is connected to a galvanometer. Whenever the switch is made on, in that case current starts flowing in it, then deflection is seen in it. But this deflection lasts for a moment and after that it stops. But when we switch the connection of this circuit, in that case what happened, then again momentarily there was deflection in the galvanometer. So he concluded that whenever there is change in current in one coil, then an EMF is induced in another coil. And so current changing can be in two ways. Number one, when switch is made on and when switch is made off. All right. There is another experiment here. This same thing you can see, so you can read it. Now we are going to talk about magnetic flux. What is magnetic flux? So magnetic flux means number of field lines. So as we have studied in case of electric flux, phi E equal to Q upon epsilon naught, which is also integration E dot ds. In same way, here we write it as phi b equal to integration b dot ds. Right. So unit of magnetic flux is Weber. Unit is Weber, and CGS unit is Maxwell. MAX, max. A relation 10 power 8 Maxwell is equal to 1 Weber. Right. So this relation you have to memorize. Now we are going to see next concept. Here flux, they are showing same thing. Now Faraday's law of electromagnetic induction can be stated as, here statement is given, the magnitude of the induced EMF in a circuit is equal to the time rate of change of magnetic flux through the circuit, that is E equal to minus d phi by dt. You can understand it that initially suppose we write the equation of flux, say phi as function of t is 2t square minus 3t plus 4, right? And suppose time is t equal to 0 and t equal to 1 second. During this time, let's see what is EMF. So EMF equal to minus d phi by dt, d upon dt of this thing 2t square minus 3t plus 4. Now we can differentiate it. So this will become minus 4t plus 3, right? And t is given as 1, so we put here minus 4 and then this will be plus 3, that is minus 1 volt. In magnitude it will be 1 volt, right? And later on there was certain modification, not modification, you can say, in case of if there is single turn in the loop, then this formula will be valid, and if there are n turns, then change the formula here, just put the number of turns minus n d phi by dt, and then you can evaluate. So if you wish to read the statement, so you can read it. The magnitude of induced EMF in a circuit is equal to the time rate of change of magnetic flux through the circuit, mathematically equal to minus d phi v by dt. Negative sign indicates the direction of EMF and hence the direction of current in a closed loop. This will be discussed in detail later on. And if there are n turns, in that case we write E equal to minus n d phi by v by dt, right? Now here there is one question. Consider the experiment 6.2a. What would be obtained? What would you do to obtain a large deflection of the galvanometer? How would you demonstrate the presence of an induced current in the absence of galvanometer? So experiment 6.2 means there is one coil, one magnet is being brought closer. That was first experiment. In second experiment there were two coils. One coil was connected to the battery, another was connected to galvanometer. So that experiment they are talking about. So here, to obtain a large deflection, one or more of the following steps can be taken. Use a rod made of soft iron inside the coil C2. If you put iron rod inside the coil, then what will happen? Induced EMF will increase, right? Here you have to put soft iron core, then connect the coil to a powerful battery. If current will be stronger, means if amount of current will be more, in that case also you will see more deflection because more current will be there. And move the magnet rapidly. If speed is increased, in that case also flux change will be rapid and hence there will be more deflection. Then comes second point. How would you demonstrate the presence of an induced current in the absence of a galvanometer? If there is no galvanometer, then replace the galvanometer by a small bulb. So bulb will glow momentarily. The kind one finds in a small torchlight, the relative motion between the two coils will cause the bulb to glow and thus demonstrate the presence of an induced current. So in experimental physics, one must learn to innovate. Michael Faraday, who is ranked as one of the best experimentalists ever, was legendary for his innovative skills. So this is basic that you have understood. Now there is another question. This question is based on the concept that EMF induced is given by minus d phi by dt. In magnitude it is just d phi by dt, and if there are n turns, in that case n d phi by dt. Now we can read the question. Question says a square loop of side 10 cm and resistance of 0.5 ohm is placed vertically in the east-west plane. A uniform magnetic field B 0.1 Tesla is set up across the plane in the northeast direction. The magnetic field is decreased to 0 in 0.7 seconds at a steady rate. Determine the magnitude of induced EMF and current during this interval. This is good question. So here we have to use one more concept. So phi flux phi B is given by BA cos theta, or B dot A as integration B ds cos theta, or integration B dot ds, same thing. So BA cos theta. In this question, theta is given as 45 degree. So if we put the value 45 and B is given in our question, so we can write B is 0.1 Tesla, area will be 10 power minus 2 meter square, and cos 45 will give 1 upon root 2. So if we simplify, what do we get? So we will get certain value. Certain value means we can simplify it. So this will become 10 power minus 3 divided by root 2. Then further, this will be 1 upon, we can rationalize it. So root 2 divided by 2 into 10 to the power minus 3, and then we write Weber. And second case is when flux is a minimum, then theta will be 90 degree. So that case they are talking about. Now here we have got the value of flux, and time is also given. It is given as t equal to 0.7 second, and we have to find out EMF. So it's simple, E equal to minus d phi by dt, but let's write its magnitude only. So here change in flux will be this much, time is this much, we can put the values. So root 2 upon 2 into 10 power minus 3 divided by time is 0.7. So we can evaluate it. This will become 1.0 into 10 to the power minus 3 volt. So we have got the value of EMF induced, and now our concern is to find current, and you know I equal to generally V upon R. In this case it will be E upon R, and induced voltage we have got as 1.0 into 10 power minus 3, and in our question resistance is given as 0.5 ohm. So we put this value. So this comes out to be 2 into 10 to the power minus 3 ampere. So I think you have understood. Now let's take another question. Another question says, a circular coil of radius 10 centimeter, 500 turns, and resistance 2 ohm is placed with its plane perpendicular to the horizontal component of the Earth's magnetic field. It is rotated about its vertical diameter through 180 degree in 0.25 seconds. Estimate the magnitudes of the EMF and current induced in the coil. Horizontal component of Earth's magnetic field at the place is given. So here some basic informations are given, and we can make use of these to calculate flux. We have to find out initial flux and then final flux, because it is rotated through 180 degree. So two cases will be there, and then change in flux we can find the difference of the two, and then after that we will find d phi by dt, and since the resistance is given we can also find current. So information is clear. So let's find out initial flux, then final flux. So phi initial is BA cos theta. Here theta will be 0 degree. So we can put the values. B is given as 3.0 into 10 to the power minus 5, and the area will be pi r square, pi into 0.1 square, and then cos theta cos 0 degree. Cos 0 degree. So cos 0 is 1. So it will come out to be 3 pi into 10 to the power minus 7 Weber. And then we find final flux when theta is 180 degree. So no other changes than this cos 180 degree. So it will become negative 3 pi into 10 to the power minus 7 Weber. Why? Logic is simple. Cos 180 degrees minus 1. And then if we find a change, so delta phi, so delta phi will be difference of the two. This second minus first, so it will be minus 6 pi into 10 to the power minus 7 Weber. And now we have to find out EMF induced, E equal to minus d phi by dt. So we divide by time and remove the negative sign. So 6 pi into 10 to the power minus 7 divided by time in our question is given as 0.25 second. So 0.25 second. And then we evaluate it. So we get 3.8 into 10 to the power. Here number of turns are also given. So 500. So this was for one turn. For 500 turns, E. So let's write it E dash. So minus n times d phi by dt. So we have to multiply by 5 to this value, and this will give final value as 3.8 into 10 to the power minus 3 volt. Right. So we have got the value of induced EMF. Now our concern is to get current. Current equal to E upon R. So we have got the value of voltage 3.8 into 10 to the power minus 3 volt divided by resistance is given as 2 ohm. So just write it 2. So we will get 1.9 into 10 to the power minus 3 ampere. So I think you have understood. Now let's see next question. Lenz's law and conservation of energy. So Lenz's law states that the polarity of induced EMF is such that it tends to produce a current which opposes the change in magnetic flux that produced it. For example, suppose you are bringing, suppose this is a coil in which there is a galvanometer here, and you are bringing the magnet north pole to this side. What will happen? The direction of current will be such that here north pole should be created, right? So current will flow like this. So north pole will be created, then what will happen? Relative motion will be slowed down or will be stopped because north will repel. Suppose you are taking this magnet away, right? Then south pole should be created so that this motion may be stopped. So the same thing is given here. The polarity of induced EMF is such that it tends to produce a current which opposes the change in magnetic flux that produces it, right? And other things we have studied, the basics, you have to just go through what all is written here. North pole is being brought closer. In that case, here north polarity is developed due to the current. If north pole is taken away, then south polarity will be developed, because of which there will not be relative motion, because if south pole is there, north pole is being taken away. In that case, force of attraction will be there. Here north pole is coming closer, so north pole is created due to the current, so obviously there will be force of repulsion. So these things you have understood, I think. Now here one more important point you have to keep in mind, that Lenz's law is in accordance with conservation of energy. Means whenever we bring this magnet, suppose we are bringing it closer, in that case work is done against the repulsive force, and that work appears in form of energy, and that causes the EMF. Similarly, if you are taking it away, then what happens? Then you have to do certain work, means there is certain work against the force of attraction, and that work is converted into energy, and that appears in form of EMF. So it is clear that there is no violation of energy conservation principle in this case, right? Here some statement is given, you can read it. A little reflection on this matter should convince us on the correctness of Lenz's law. Suppose here they are saying that suppose that the induced current was in the direction opposite to that one depicted, right? Suppose we are taking this north pole away, and here there is north pole. In that case, what will happen? This motion will continue non-stop, and that is not possible. So in that case, the south pole, due to the induced current, will face the approaching north pole of the magnet. The bar magnet will then be attracted towards the coil at an ever increasing acceleration. Here in this case, suppose there is no north pole. In that case, what will happen? Here south pole will be there. So there won't be any repulsive. Continuous attraction will be there. So if speed will go on increasing, so continuous acceleration will be obtained. So here the bar magnet will then be attracted towards the coil at an ever increasing acceleration. A gentle push on the magnet will initiate the process, and its velocity and kinetic energy will continuously increase without expending any energy. So if this can happen, one could construct a perpetual motion machine by a suitable arrangement. This violates the law of conservation of energy and hence cannot happen. So it is obvious that there should be opposite polarity when when magnet is brought closer. In that case, there should be same polarity, so that relative motion may be minimized or it can be stopped. Similarly, if magnet is taken away, then whatever pole is closer to the coil, so just opposite pole should be developed due to the flow of current. So this thing you can easily understand. I think is very clear. Now we are going to see some more concepts here. If sorry, if this coil is if this loop is taken inside, this loop is taken outside, here this is being taken outside, so there is flux change. So this flux change will give rise to the current. So we have to tell the direction of current here. So the same thing is in here explained. The magnetic flux through the rectangular loop ABCD increases. Here it was outside, now it is being brought inside the magnetic field. So definitely flux will increase and hence there will be a current. So here motion of the loop into the region of the magnet, the induced current must flow along the path BCDAB so that it opposes the increasing flux. So BCDAB. So current, when it is being brought inside, then direction of current should be like this, right? Then second one, in this case what happens? Here direction of current was like this when it was being brought inside. Now it is taken away, then what will happen? Will the current be like BCA AB or ACBA? So that thing we are going to see. So due to the outward motion, magnetic flux through the triangular loop ABC decreases, due to which the induced current flows along BACB, right? In previous case, so this is just opposite. And then comes, in this case what happens? You are taking it away. When you are taking it away, then direction should be DCBA or ABCD. Which one? So as the magnetic flux decreases due to the motion of the irregular shaped loop ABCD out of the region of the magnetic field, the induced current flows along CDABC. CDABC. Like this, right? So these things you have to understand. Now there are some more questions, like A closed loop is held stationary in the magnetic field between the north and south poles of two permanent magnets held fixed. Can we hope to generate current in the loop by using very strong magnets? So, as you have studied that there will be induced EMF only when there is relative motion. However strong magnetic field is there, that is irrelevant. So here answer is no. However strong the magnetic field, current can be induced only by changing the magnetic flux through the loop. Alright. Then comes second question. It says a closed loop moves normal to the constant electric field between the plates of a large capacitor. Is a current induced in the loop when it is wholly inside the region between the capacitor plates? When it is partially outside the plates of the capacitor, the electric field is normal to the planes of the loop. So let's see the situation. Here, what is happening? Here, this is the case. Right. So the induced EMF is expected to be constant only in the case of rectangular loop. This is being taken out. This is also being taken out. But what is happening? Here, this is rectangular loop. So in which case change will be higher. The induced EMF is expected to be constant only in the case of rectangular loop. In the case of circular loop, the rate of change of area of the loop during this passage out of the field region is not constant. Hence, induced EMF will vary accordingly. Right? And last case is predict the polarity of the capacitor in the situation described by figure. So here again, this is approaching. So what should be the polarity? What type pole should be created in this loop? So south pole should not approach this, right? So here there should be south pole, here there should be north pole, right? So the polarity of plate A will be positive, this will become positive, and that of plate B will be negative. So current will flow like this. So from this side, if you observe, south pole will be created. From this side, if you observe, north pole will be created. Hence, relative motion will be minimized. Now, we are going to see motional EMF. What is motional EMF? Here, there is a magnetic field perpendicular to the plane, and in downward direction, this is conducting rail. This length is L, and this is rod which can move. If this rod moves in this direction with a velocity v, in that case, what EMF will be produced? So in order to find EMF induced, first of all, we have to find out what is flux in this position. So in this position, we can find flux by using formula phi equal to B times A. Here cos theta, we don't have to consider. Theta will be 0 degree because both will be along same line. So here just we write B into A. Area in this case, this is width or this is length, this is width. So Lx. So we just write phi equal to BLx. Is it clear? Phi B equal to BA, we are applying here, A is Lx. Now we need EMF, so that is minus d phi by dt. So here differentiable term is just x because this can move, so L here x can decrease but L will remain same. So B, keep minus sign, BL dx upon dt. And if you remember, dx upon dt is velocity. So we can include that negative sign here also. So we can replace minus dx by dt as v, because here x is decreasing. So that is why minus sign is involved in it. So we have got motional EMF as BLV, means magnetic field strength, length, and velocity with which conductor is moving. Right. So this is called a motional EMF. Here this conductor is in motion in magnetic field, right? So description is given here, you can easily understand. Next thing comes, here same thing they have written as work done, then charge is moving. So this is another way of explanation of same thing, that on charge, that on the rod PQ charge will get accumulated on one side, and then we can find the EMF. Let's read it. It is also possible to explain the motional EMF expression previously obtained, that was E equal to BLV. So other way around, if we consider that this is a rail and here this is conductor which is moving in this direction, and there is magnetic field, right? So it is moving with velocity V, and this distance projects, this is L. So here what happens, charge on this conductor will get accumulated. So that concept we are going to study. It is also possible to explain the motional EMF by invoking the Lorentz force acting on the free charge carriers of the conductor. So if you remember, Lorentz force F equal to QVB. So here consider by invoking Lorentz force free charge carriers of the conductor PQ. This conductor, this is PQ that you have seen in the diagram, the same thing. Consider any arbitrary charge Q in the conductor PQ. Here we consider a charge Q. When the rod moves with velocity V, the charge will also be moved with velocity V in the magnetic field V. The Lorentz force on this charge is QVB, as you know very well. So QVB in magnitude, and its direction is towards Q, right? It will move up. All charges experience the same force in magnitude and direction, irrespective of their position in the rod PQ. The work done in moving the charge from P to Q is, it will be equal to how much? So force into displacement. So force is QBV, displacement means length of this PQ, that is L. So we can write this W equal to QVBL. Now if you remember, potential is defined by W upon Q. So here if we divide this equation, W equal to QVBL by Q, we will get potential or EMF. So W upon Q, that this gives a BLV. This is same expression as we have obtained earlier. So this is another way of finding EMF induced due to motional. Here we have found motional EMF means what is happening? The conductor is moving in a uniform perpendicular magnetic field. So if you remember, the force F is given by F equal to QE plus V cross B, right? And what is the name of this force? Do you remember? Lorentz force, right? Lorentz force. When charge is moving in magnetic field as well as in electric field, in that case this force comes into play, and that is given by QE plus QVB. Now if there is no velocity, then what will happen? This term will vanish. Only F equal to QE will be there. So that thing is explained here. And other things you can read, it is simple. Now let's see one important question. A metallic rod of 1 meter length is rotated with a frequency of 50 revolutions per second, with one end hinged at the center and the other end at the circumference of a circular metallic ring of radius 1 meter. About an axis passing through the center and perpendicular to the plane of the ring. A constant and uniform magnetic field of 1 Tesla parallel to the axis is present everywhere. What is the EMF induced at the center and at the center of the metallic ring? So let's see. This question is important. You must know. It has been asked many times in CBSE exam. So first of all, let's see what all is happening. So this is the case. This is metallic ring of radius r, and this is a rod that is moving like this, right? So at any instant, if we see what is theta, theta is omega t, and then we can find angular velocity, right? So from here d theta by dt, and then other things we can calculate. So here there are two methods of calculating the EMF induced. So we will see one by one, and we will try to find out why these two methods are important. So in first case, we take the rod is rotated, free electrons in the rod move toward the outer end due to the Lorentz force, as we have seen in previous case, and get distributed over the ring. Thus, the resulting separation of charge produces an EMF across the ends of the rod. Right? What is happening? If you consider this rod, so all charges are accumulated here. They move like this. So there will be potential difference. They are saying the same thing. At certain value of EMF, there is no more flow of electrons. Maximum charge is accumulated here. In that case, no more flow, and a steady state is reached. So magnitude of the EMF generated across a length dr of the rod. In previous case, we can consider here take small length dr. So across dr of the rod, it moves at right angles to the magnetic field. Magnetic field is perpendicular downward. So it will be equal to dE equal to BV dr. Right? So dE equal to BV dr. And then we can put V equal to R omega, and limits we can put E equal to integration BV. V can be written as R omega and dr, and we put the limit 0 to R, because here the rod is fixed at this point and radius is R, and this is rotating like this, right? So if we evaluate it, this will become B omega R square by 2, and we can put this capital R. So we will get this value B omega R square by 2, right? And we know V equal to R omega that. And in our question, information is given, B is given, omega is 2 pi into, what is formula? Omega equal to 2 pi by T. So we can put the value of frequency is given 50, if you observe. So that is why 2 pi 50 into, then radius, this rod length of rod is given as 1 meter, so we put 1, and we get 157 volt. Is it clear? So here, what is problematic? Is this problematic? Why problematic? Because you have studied motional EMF, BLV. Here what we are doing, we are taking L as dr, right, and E as dE. So dE equal to B, and let's write V earlier, and then we write it dl, and then to find total EMF we can integrate it. So when we integrate, so we will get E, and then we put limit 0 to R, and then BV. So here L can be put as dl or dr. So if we are taking it as dr, no problem. And then V equal to R omega we can write, and after that we can integrate. So I think it is clear. Now there is another method. Another method is simple. In this method, we are going to see that area of sector. So what portion it will move? If suppose it makes angle theta, we are checking like this. So suppose this is theta. So area of sector, if you remember, what is formula? Area of sector is theta upon 360 pi r square. Here let's write 360 as 2 pi. So theta upon 2 pi, then into pi r square, right? So what is left? So we will get pi will cancel out, theta r square by 2. So same thing is given here, pi r square theta by 2 pi. So this expression where r is the radius of the circle. Now we have to find out the value of EMF. So EMF can be found by formula E equal to d upon dt of phi, or d upon dt of phi. Phi is b and b is fixed, and area we have found as 1 by 2 r square theta. So here differentiable term is theta only. So half b r square outside d theta by dt, and if you remember d theta by dt is omega, so we get 1 by 2 b r square omega. So this is another method of finding same thing. I think thing is clear. Now there is another question in which same formula is to be applied to get induced EMF. So question says a wheel with 10 metallic spokes, each of 0.5 meter long, is rotated with a speed of 120 revolution per minute. So here number of revolution per second will give frequency, and then we can find omega 2 pi times frequency. And the horizontal component of pulse magnetic field He at a place which is given to 0.4 Gauss at the place. What is the induced EMF between the axle and the rim of the wheel? Note that 1 Gauss is 10 power minus 4 Tesla. So you know very well that formula value will be 1 by 2 omega times br square. So 1 by 2 omega times br square. Radius is how much? 0.5 square, and we put the values of omega 2 pi times number of revolution per second. So revolution per second will be equal to 120 divided by 60, so it will become 2. So that is why this is 4 pi, and then area by r square. What is the radius? The radius is given 0.5. So here value of magnetic field, it is given as 0.4 into 10 power minus 4, 0.4 Gauss. Did you understand? There is problem. If problem, we can evaluate. Omega is equal to 2 pi times frequency, right? 2 pi times number of revolutions per second, 120 revolutions divided by 60, so this will give 4 pi. So that is why the term 4 pi is used, right? So after evaluation we will get 6.28 into 10 power minus 5 volt. Clear? Now we are going to see inductance. So what is inductance? So this is stated here. An electric current can be induced in a coil by flux change produced by another coil in its vicinity, or flux change produced by the same coil, right? These two situations are described separately in next two subsections that we will study. However, in both the cases, the flux through a coil is proportional to the current. So the main concept is flux is proportional to current. So phi is proportional to I, or phi equal to Li, right? Where L is coefficient of inductance, coefficient of induction, that is, this is inductance, right? L is inductance and its unit is Henry, right? Henry. So if we want to find out EMF from here, so we write E equal to minus d phi by dt, d phi by dt. So minus L di by dt, correct? So you will find certain questions sorry, where change in current will be given, L will be given, and you have to find out induced EMF. So you can easily do that. If there will be n turns, then we can say that n phi b equal to I, and then we can easily evaluate. So we will see other cases soon. Now, mutual inductance. If there are two coils with the number of turns n1 and n2, and one carries current, then we can find the relation. So let's analyze it. So first of all, let's see the diagram. This is important derivation. You have to be very careful. Here there are two coils. One is S1, another is S2. One has turns N1, another has turn N2. The radius of inner coil is R1, radius of outer coil is R2, but for calculation purpose, we always take inner radius and not that of outer one. So that is one important point. Here we are going to find out the coefficient of mutual inductance M. By same concept, generally M, here also we say that flux change in one coil due to other is proportional to current, and when we write the relation, so phi will be equal to Mi in this case also, or d phi by dt, which is EMF induced, is, we can say, minus d phi by dt, which is EMF, so minus m di by dt. So this is same, and unit is also same as we have seen for L, that is Henry. So unit of L or unit of M, coefficient of self-inductance, coefficient of mutual inductance, coefficient of self-induction or self-inductance. This is coefficient of mutual induction or mutual inductance. Both have units Henry, right? Now we are going to derive the expression for M. So here we will denote it as M12 or M21. Both will be same, and they will depend on the number of turns in both the coils, current, and the material that they contain inside. So let's see the derivation, but you have to be very careful. When a current I2 is set up through coil S2, it in turn sets up magnetic flux through S1. Of course, when current will flow in one coil, then there will be magnetic flux in another coil. So let us denote it by phi 1. The corresponding flux linkage with solenoid S1 will be number of turns in it. So in first coil there are n1 turns, so n1 phi 1 must be equal to, as I told you, that phi depends on current, and we can write the coefficient of mutual inductance as M12, and then I2 is the current, right? Similarly, just opposite way, if we write, we will get another relation, N2 phi 2 equal to M21 and I1, right? But so here this M12 is also referred as coefficient of mutual induction. For these simple coaxial solenoids, you have seen the axis of the two coils is the same. So for these simple coaxial solenoids, it is possible to calculate M12. The magnetic field due to the current I2 in S2 is, if you remember the expression, B due to solenoid is given by mu naught Ni, where N is number of turns per unit length. So length is L and the number of turns is N1. So here small n1 can be found by N1 divided by L. So the same thing we can write. So here this is magnetic field, mu, this formula, mu naught, then N2 I2, because current is flowing in secondary solenoid, all right, and here BA. So this is B and the area per turn, right? So total area we have to consider, because there are here many terms in length L. So that is why we should write it as N1L times pi R1 square times this. We simplify, we get this relation, right? Now, if we compare this relation and this relation, what do we observe? Clearly, I2 you can ignore, then remaining things will be M12. So we can get M12 like this, mu naught N1 into pi R1 square L, right? Here, we are taking some approximation like L is greater than R2. So we can consider another situation. Now we consider the reverse case. In this case, current I1 is passed through the solenoid S1 and the flux linkage with coil S2 is calculated. So as in previous case, we have written N1 phi1 equal to this thing, all in terms of N1. These are in terms of first coil, and this is magnetic field due to second. So in this case, we have to write the magnetic field instead of second, magnetic field due to first. So here mu naught N1 I1, and then since flux linked with secondary coil is to be found, so we have to take the area. But keep in mind, as I told you, even if area enclosed by secondary coil is more, but we always consider the inner coil. So that is why area will not change. It will remain pi R1 square. But length is common length, that is also N2L, right? Number of turns per unit length, and length is L. So from here, again we can get the value of, if we make comparison from here, N2 phi 2 equal to M21 I1, and here we have got N2 phi 2 equal to this much times I1 term you can neglect, then whatever is left, that will be value of M21. If you observe carefully, M12 equal to mu 0 N1 into pi R1 square L, and here mu 21 is mu 0 N1 into pi R1 square L. Both are same, right? So we say that M12 equal to M21, right? So this is coefficient of mutual induction. Now, so we can write it in general form. We are going to drop here the script. So M equal to mu 0 N1 into pi R1 square L. And if there is some material, some medium in between the coil of relative permeability mu r, if relative permeability is mu r, in that case we have to multiply by mu r to the expression of coefficient of mutual inductance, that is M equal to mu r mu 0 N1 into pi R1 square L. So I think you have understood. Now let's see this question. Question says two concentric circular coils, one of small radius R1 and the other of larger radius R2, such that R1 is less than R2, are placed coaxially with the centers coinciding. Obtain the mutual inductance of the arrangement. So let the current I2 flow through the outer circular coil. The field at the center of the coil will be B2 equal to mu 0 I2 divided by 2R, right? And since the other coaxially placed coil has a very small radius, B2 may be considered over its cross section area, then phi 1 we can find. So phi equal to area times magnetic field, pi R1 square B2, right? But here we have got value of B2 as mu naught I2 divided by 2R2. So we write that value over here. So we get this value M12 times I2. This value will obviously, after putting that value, we compare it phi 1 equal to M12 I2, right? So we can say M12 will be this much. Then M21 is also same. So note that we calculated M12 from an approximate value of phi 1, assuming the magnetic field B2 to be uniform over the area pi R1 square. However, we can accept this value because this. So here it shows that varying current in a coil can induce EMF in neighboring coil. The magnitude of induced EMF depends upon the rate of change of current and mutual inductance of the two coil. So once again, I would like to tell you about this question, and after that we will continue these all derivations. So here the question says two concentric circular coils, one of small radius R1 and the other of large radius R2, such that R1 is less than R2, are placed coaxially, means their axis is same, with centers coinciding, center of the two are same. Obtain the mutual inductance of the arrangement. So as I told you earlier, that we assume that current I2 flows through the outer circular coil. So this will give rise to the magnetic field at the center. So since current is flowing through secondary, so we write magnetic field in terms of secondary. So we write just B2 equal to mu naught I2 divided by 2R. So here there will be a question in your mind, why this formula? So if this is coil at its center, what is formula of magnetic field? B is given by mu naught I divided by 2R. If R is radius, then this is formula. The same we have applied here, that B2 will be mu naught I2 divided by 2R2, right? So now I think you have understood. And then flux linked with primary, suppose we want to find out, in that case we write area primary times magnetic field due to secondary. So pi R1 square B2, and then we put the value of B2, we get this relation, but we can write phi1 equal to M12 I2. So we have got the value of M12, right? And we know that M12 equal to M21. So this is expression for coefficient of mutual inductance. So that was our purpose. Other things we will study in next lecture. Thank you for watching. Team Educate.